Okay, this will be lesson 2 of chapter 7, and in chapter 7 we've been talking about the periodic table trends, and today we'll begin talking about ionization energy. Let's define this first. Ionization energy is how much energy it takes to remove an electron from the ground state of a gaseous atom. So essentially it's a measure of the heat necessary to remove an electron, and this will be given in kilojoules per mole, usually, just like kind of we've been used to in chapter 5. So the first ionization energy measures how much energy it takes to remove the first electron. So this is, you can write the equation looking like this. Here's sodium elemental, and here it's lost its electron. The second ionization energy, now we have sodium plus, now we're removing the second electron. And we can talk about the third, the fourth, and so on. And this is the definition of ionization energy. How much energy it takes to ionize the element. And by ionize, we mean make it into a plus charge, positive charge. If you take a look, we have here a graph, and what they've done is they've actually separated the place at which the amount of ionization energy jumps enormously. So if you take a look, sodium's first electron is about 495 kilojoules per mole, but then it jumps tenfold almost to 4,500. If you look at aluminum, aluminum is 578 up to 1817, 2745, and then all of a sudden you have a huge jump to 11,000. What they're showing you here in this stair-step configuration is when you go from the white to the blue, what you're doing is you're removing a core electron. So all of these are actually outer electrons, and then these are your core electrons. Anytime you try to remove a core electron, the amount of energy to remove it just spikes significantly, is the idea. So in general, here it says it requires more energy to remove each successive electron, which makes sense. When you remove a second electron, more energy than the first. You can see that with aluminum. You know, this was 578, you got 1817. That's understandable. But the huge jump, what we can call a quantum leap, occurs between the valence and the core electron, and that's true in any sense. Look at here at phosphorus from 6,000 to about 21,000. That's a pretty big jump, pretty significant jump, and that's because you are removing a core electron in this transition. So in general, the trends, as you can see in this graphical depiction, are as you go toward the right, you increase the ionization energy as you go across a period, and as you go up a group, you also increase in ionization energy. So helium, for example, if you take a look, has the highest ionization energy. If you recall, helium was also the smallest. Helium was the smallest of the atoms, which means the smaller you are, the harder it is to remove electron, which is true. And then same thing with cesium, even though we had francium down here, but we're removing the last period here. Cesium has the lowest because it is the biggest. And that's the idea. So ionization energy essentially mirrors the atomic size trends. However, I would like to call your attention and the attention of all your friends that are with you to a little discrepancy here. So take a look at this portion right here, and this portion, and then this portion as well. So in general, as we go across a period, we increase. However, there is actually a decrease between beryllium and boron. There's also a decrease between nitrogen and oxygen. These decreases are very important, and we'll have to actually talk about them. The reason there's a decrease in this area, notice a similar thing happens between magnesium and aluminum, and then calcium and gallium, and the further down you go, the less of this you see. But the reason here is because we're going from the S subshell to the P subshell. So once you have these elements here actually have a fully filled, it's getting a bit nauseating. Let me try it this way. This is your S, and this is your P. So these elements actually have a fully filled S subshell. And then here, what they have to do is they have to open up their P subshell. And recall we said you have extra stability for filled subshells. So because here we have filled subshells, you get extra stability, so you get a higher ionization energy. It's tougher to remove beryllium's electron because it's more stable than it is to remove boron's electron. The division here is whenever you're going from nitrogen to oxygen, nitrogen actually has a half-filled p subshell. So it's 2p, for example, is half-filled. Being half-filled, you get extra stability. So oxygen, it's easier to remove oxygen's electron than it is to remove nitrogen, because oxygen actually has an extra electron paired up, which creates some repulsion and not as much stability is the idea. So this, in general, this actually proves or leads us to give some support to our idea of subshells and our idea of orbitals and filling orbitals with electrons. So this picture right here actually confirms our understanding of subshells and orbitals that we talked about in chapter 6. So chemistry wins again. And this is essentially the explanation for it. So as you go down a group, less energy is required, so ionization energy decreases. And the explanation for this is that the valence electrons are further from the nucleus. The effective nuclear charge remains the same, but the electrons are further and further and further away from the nucleus, and that's essentially why. And as you go across a period, the effective nuclear charge increases because, again, as before, you have an increasing number of protons creating a stronger and stronger nuclear charge, which means the electrons are pulled closer, which means it takes more energy to pull them off, is the idea. If you do the same thing, if you graph, you'll definitely see a trend, but in this trend you'll be able to see these discrepancies. So this discrepancy here is the transition between the S to the P subshell, and this discrepancy here is the half-filled P subshell. You can also see it here, and then it becomes less distinct, but you can definitely still see it. And as you go across, it becomes less and less distinct. But these anomalies are actually very important to understand and be able to explain. And you would explain it with extra stability for a half-filled or a fully filled subshell. And this is, I think, is another explanation of it essentially. So this kind of explains what we've just been talking about. So no need to explain it one more time. Just take a look at this, pause it, and enjoy it, and then we'll move on. So now we can arrange them as we've done with atomic size. We can arrange elements in order of increasing first ionization energy. So what we'll do is we'll list them from the from the easiest to the hardest to remove. So essentially this is going to be from biggest to smallest. So if you take a look on our periodic table, let's take a look at which elements this refers to. So here we have neon, we have sodium, we have phosphorus again, we have argon, and we have potassium. So because the smallest one is neon, neon will take the most energy to remove an electron from. The biggest one is potassium, so potassium will therefore take the least. So essentially we're going to list them from the biggest to the smallest. In this case, we'll say potassium. Now if you take a look, who is bigger, sodium or argon? Definitely sodium. So we'll do potassium, sodium, and then we'll do phosphorus, argon, neon in that order. So we got potassium, sodium, then phosphorus, then argon, and then finally neon. So neon wins. Neon takes the most energy to remove an electron from, and that's kind of the idea. The last trend we'll talk about here will then be something called electron affinity. Now let's define this just like we've defined the previous one. Electron affinity is the energy change when a gaseous atom gains an electron. So whereas ionization energy looked at losing an electron, electron affinity looks at gaining the electron. And essentially whenever you give an electron to an atom, it becomes more stable. especially with nonmetals. So now electron affinity can be either exothermic or endothermic. Remember we said that ionization energies are always endothermic. You always have to put energy in to remove electrons. So IEs are always endothermic because if you want to remove an electron, you have to use energy to remove an electron. For electron affinities, they can be positive or negative. If the element gains stability, then it will release energy. You can think of it as releasing or as thanking you and giving you off some energy. Sometimes, if you're a noble gas, you are stable already. You do not want an extra electron. So you can make the argon receive that electron, but it'll cost you energy. This is an endothermic process because it goes against what argon wants to do, or against the stability of argon is the idea. And in general, what you see, electron affinity becomes more exothermic as you go from left to right. So in general, you begin negative 60 and you end at negative 328. And the trend, this trend is actually not as perfect, but you can definitely see the exceptions. First of all, you see that all the noble gases have a high electron affinity, which says that they are stable. They do not want that extra electron. In fact, you'll have to put energy. The fact that a delta H for these is greater than 0 means that delta H is positive, which means you have to put energy into the atom in order for it to accept an electron. A similar thing happens here for the S block, and that's because beryllium has a filled S subshell. So again, we see this extra stability with filled S subshell. You also see the discrepancy here between nitrogen and oxygen. Interestingly, nitrogen has a positive. Nitrogen also does not want that extra electron. And again, that's because nitrogen has a half-filled shell, or subshell. So nitrogen here is half-filled. So that's kind of the idea. And the trend in general is seen if you were to graph it. I don't think we have a graph, but we do definitely have the explanations here. So this is the same explanation as we've just seen, just restated. So feel free to go through it, and you see the discrepancy in the half-filled area here, and you see this discrepancy in the fully filled subshell. And obviously you see the discrepancy here. This is the fully filled shell. Once the shell is completely filled, you definitely get some stability. And that's why the noble gases have very high electron affinities. And I think that will wrap it up. I think we'll talk about metals next time. We'll actually begin this discussion. So this one's a shorter lesson. So this is lesson 2 of chapter 7.